Even the most complex reaction pathways like gluconeogenesis or the Krebs cycle are actually just collections of individual reaction steps. Furthermore, some of those steps happen faster, some happen slower, and the MCAT can test you on all of this knowledge. I'm Tyler Farah, and in this lesson, we're going to take a deep dive into reaction mechanisms and the rate laws that govern them, because that's going to help you out not only in the Chem Phys section, but also in Biochem. In particular, we're going to take a look at what are called elementary reactions, which is the fancy name for the individual steps of any mechanism. And what we'll learn is good news. While mechanisms themselves can be fantastically complex, the individual steps that make up these mechanisms are very limited. Take a moment and read through this question stem right now. So while this question stem mentions the SN1 reaction, the focus of this question stem is actually to teach you a little bit more about reaction rates and mechanisms in general. In particular, Sir Christopher Ingold, the researcher that's mentioned in this, actually has two main conclusions. The question stem asks, how can he prove, using his data, that carbocation formation is the rate determining step? But implicit in that major conclusion is another secondary conclusion, which is that the SN1 reaction is a multi-step reaction mechanism in the first place. And actually, you can prove that this is a multi-step reaction mechanism just by looking at the reactants. In our overall reaction schema, there are 1, 2, 3 different reactants. That fact alone is enough to prove that this must be a reaction mechanism consisting of more than one step. My first question for you is why? Why does the fact that there are 3 different reactants prove that this SN1 reaction must be a multi-step mechanism? The answer comes from what's called the collision theory of reaction. In this theory, the central assumption is that for molecules to react, they have to bump into each other in space or in solution. You can imagine the odds of 3 separate molecules all bumping into each other at the same time, in the same place, in the right orientation, with enough energy to react. Those odds are like astronomical. So according to collision theory, in an individual reaction step, you're never going to see 3 molecules as the reactants. With that in mind, let's turn our attention next to the kinds of elementary reactions that are possible that make up the steps of any reaction mechanism. Our first prompt question asks us to examine the different kinds of elementary reaction steps that are possible. You can see here that there are only 3 rows in this table, and that's good news. What that tells you is that when it comes to a multi-step reaction, there's actually only 3 kinds of individual reaction steps. The first possibility is what's called a first-order elementary reaction. We start with a single reactant. What I'd like you to do is think about what that single reactant could do in a reaction step, and then also capture the rate law that would be associated with such a reaction. By far the most common thing that a single reactant is going to do is to split apart. You actually see this all the time and you might not even recognize it. For example, if you take some acetic acid and you throw it into solution, the first thing it's going to do is deprotonate. Well, that is actually a single molecule splitting apart into 2 products. Now, as for the rate law associated with this elementary reaction step, that's going to be equal to K, a constant, times the concentration of the original reactant raised to the first power. What this tells us is that it actually doesn't matter what the products are. And in fact, other kinds of first-order reaction are possible. This is just the most common one. But the point is, no matter what that single reactant does, it's always going to have the exact same rate law because only the reactants influence the rate of reaction. Now, you might be looking at this and saying, well, wait a minute, Tyler. I thought that for exponents and rate laws, these had to be experimentally determined. And you're exactly correct for overall reaction mechanisms. But the brilliant thing about these elementary reaction steps is that their rate laws are mathematically determined. How those steps combine to give an overall rate law, you can't predict without doing an experiment. But for any given step within a reaction mechanism, you know the rate law because it's set in stone based on the kind of step that you're looking at. Given the information that a first-order reaction step involves 1 reactant, you might predict that a second-order step involves 2 reactants. And again, there's only 2 possible ways that 2 reactants can interact. go ahead and jot down the two possible reactants in the reactant column of this table. You can have two different reactants, or you can have two of the same reactant. Let's focus on the first case, X and Y, and think about what the rate law for this reaction might be. In fact, record that in your lesson book. When it comes to two different reactants, they might combine to give us a new product, in this case Z, and we'll see an example of a step exactly like this in this lesson. It's important to point out other kinds of products are possible when we have two different reactants coming together, and we'll see an example where we do get a different kind of product in this lesson as well. But I want to point out it doesn't really matter what happens on the product side of these reactions, because for any rate law, the rate only depends on the reactants. In this case, because we have two different reactants, X and Y, the concentration of both X and Y is going to influence the reaction. And again, both of those are raised to the first power. This is mathematically determined, no need for experimentation. Think about it though, this makes a lot of sense. According to the collision theory, in order for X and Y to react, they have to collide in space. Well, if I have more molecules of X or more molecules of Y, both of those are going to make it more likely that they collide, increasing the rate of this reaction. You also know that some reactants are simply more likely to react once they have bumped into each other. That's the role of K in these rate laws. For reactants that are very reactive, we would expect that reaction to have a large constant, which will further increase the rate of the reaction. Only one rate law left. Let's take a look at the other kind of second-order reaction step where two of the same reactant come together. Predict what the rate law would be for this last kind of elementary reaction step. Here again, we'll depict X and X coming together to make a new product Y. And again, other products are possible, but it doesn't really matter for rate laws because only the reactants influence the rate of a given reaction. In this case, the rate law would be given by another constant times the concentration of each of the reactants. But the twist is that because the reactants are the same, algebraically we can combine them into rate equals kx squared. As with the last example, increasing the concentration of the reactant or increasing K, implying that they're just more reactive reactants, either of those will increase the overall rate of reaction. All right, now it's time to roll up your sleeves and get your hands dirty applying these ideas to an actual reaction mechanism. The famous first step in an SN1 reaction is carbocation formation. And again, you've probably already memorized that this is the rate-limiting step in an SN1 mechanism. What we're out to do is prove why that is using experimental data. So what I'd like you to do for this first step is consider what kind of reaction this is. Is it first order? Is it second order? And if it's second order, what kind of second order reaction? And based on that conclusion, also assign a rate law for this first step. This first step begins with a single reactant. In this case, the leaving group leaves, taking some electrons with it, and that leaves behind the carbocation intermediate as well as that freestanding leaving group, which now carries a negative charge. The important thing to observe here is that, again, for assigning rate laws and reaction step types, it's only the reactants that matter. And the fact that there's one reactant here makes this a textbook first order step. In fact, just like our example from earlier, that one reactant is splitting into two products. Given that information, we know that the rate law, which again for an elementary reaction step is mathematically determined, that rate law must be some constant times the concentration of the reactant raised to the first power. But before we move on to the next step, let's spend a second thinking about what these numbers mean. We already know from our outside studies that the rate of this is going to be very low because this is the rate determining step. That means one of the variables on the right-hand side must be quite small as well. Now, the concentration of the reactant can be varied by the experimenter and certainly will be. But for this to consistently be the slowest step in the reaction mechanism, it must have a very small rate constant associated with it as well. Why would you expect that carbocation formation should have a small rate constant even without doing an experiment to measure that rate constant? The answer is that in order to generate a carbocation intermediate, we have to go from a reasonably stable reactant to a highly unstable product. This isn't likely to happen spontaneously. And the point of this exercise is that qualitative observation about the reactivity of our reactant is actually captured in the mathematical rate law as well. Step 2, nucleophilic attack of our carbocation intermediate. Using what you know about elementary reaction types, take a look at this step and also assign a reaction order and think about what the rate law for this step should be as well. In this step, we have two different reactants. You might call them X and Y. Our nucleophile attacks our electrophile and they combine into one more intermediate product. This is a textbook second-order reaction step. It's just like the one we saw in a general format on the previous page, and so we know the rate law must be some constant times the concentration of the two reactants. Here again, we can see how some of our qualitative observations about this reaction step would be reflected in the rate law. You probably know from your outside studies that this rate is going to be very high. Yet one thing to observe is that the concentration of carbocation itself is probably going to be quite low at any given time. Again, I want you to think about why the concentration of carbocation would be so small and how mathematically the rate law for this could still be very large, such that step 2 is not the rate limiting step. Go ahead and record those observations in your lesson book right now. The reason why the carbocation concentration in this second step is probably going to be very low is again due to the carbocation's inherent instability. That means that both in step 1, we're not likely to make much carbocation very rapidly, but also in step 2, we're going to take what carbocation we do have and rapidly react it away. The point is, in this step, there's probably not a lot of carbocation present. And yet, we know that step 2 is not the rate-limiting step, which means its rate must be quite large. This is captured again in the reaction constant. K2 for this step must be very big to compensate for the fact that the carbocation concentration is so low. Overall, this step must have a very large rate. All of this leads us to the last step in this SN1 mechanism, deprotonation. Again, in this case, consider what kind of reaction step this is and assign a rate law appropriately. Here we see something just a little bit different than we've seen so far in this lesson. Again, we have two different reactants, and our solute is going to deprotonate that intermediate to form our final product. But in this case, rather than the two reactants coming together to form one new product, we see that there are actually two new products. This is another way that a second-order reaction might play out. But the point is, for our purposes in calculating rate laws, it doesn't actually matter. All that matters are the kind of reactants involved when we're dealing with a rate law. So the rate law for this would again be some kind of a constant times the concentration of the two reactants involved. In this case, the rate is certain to be extremely high, irrespective of what the K value is. Why? In this reaction step, water isn't any happier to carry a positive charge than is the original oxonium reactant. So you might not expect the rate constant to be very large for this step. However, water is the solute. There is tons and tons of water around, almost an inexhaustible amount. And for that reason, you would expect the rate to be extremely high overall. Putting all of this together, we've justified qualitatively why carbocation formation should be the rate determining step. And it's very likely that Sir Christopher Ingold had a similar suspicion as he developed this mechanism as well. But remember, if we want to calculate the rate law for an overall mechanism, we can't do that mathematically. The only way to know a rate law for an overall mechanism, that is a collection of these steps, is to determine it experimentally. What we're going to see is that the experimental data backs up our suspicion that the first step is the rate determining step. All right, we've saved the best for last. This information about calculating a rate law for an overall mechanism is routinely tested on the MCAT. So let's get a little practice to make sure that you're comfortable with this process. Using what you know about computing rate laws, go ahead and compute the rate law for this mechanism right now. if you're not sure exactly how to do that, don't worry about it. We're going to cover that procedure in just a moment. The procedure for calculating rate laws for mechanisms given experimental data is very formulaic. Basically, we're going to start with one reactant and we're going to change its concentration. Notice that between trials 2 and 3, the concentration of the other reactant remains unchanged. And the effect of doubling this reactant's concentration is that we double the rate. That tells us in our rate law, this first reactant definitely plays a role. And in fact, the 1-to-1 ratio, double the concentration, double the rate, tells us that the exponent has to be 1. Repeating this procedure for ethanol, our second reactant, we're going to change its concentration while holding the first reactant's concentration constant. And in this case, ethanol plays no role in the reaction's rate. One way to represent that mathematically is to say that ethanol has an exponent of 0. Of course, that cancels ethanol out of the rate law entirely, so that the final rate law is a constant K times the concentration of the original reactant. One last question for you. Overall, how does this data prove that the first step, carbocation formation, is the rate determining step for an SN1 reaction? I'd like you to answer that question right now. Observe that our final experimentally determined rate law is exactly equal to the rate law for the first step. This tells us that whatever the rate law for the first step is, it must be the slowest step overall, since it literally and mathematically determines the rate for the whole reaction mechanism. In short, these experimental data support our original hypothesis that carbocation formation is the slowest step because forming a carbocation is so hard to do in the first place. Having learned in this lesson that there are really only 3 kinds of individual reaction step, that is one where a single reactant reacts, one where 2 different reactants react, or one where 2 of the same reactants react, I challenge you now to go back and take a look at some of those really complicated biochemistry mechanisms. With the fresh perspective that you've gotten here, you're going to see these same patterns start to emerge, and that's going to help you learn those more complicated mechanisms as well.